Hello and welcome to MAI HLSL course. For the topic 5, we are going to cover SL 5.1 subtopic today, which is introduction to the concept of limits as well as derivative interpreted as gradient function and as a rate of change here. Okay, so let's start with the calculus. We divide calculus into two parts, differential calculus and integral calculus that we are going to cover in this topic 5. The branch of mathematics that deals with the continuous change, not the discrete change, is the calculus. Okay, consider this situation where the time versus distance graph is given to us like this. So in this calculus, we are going to learn how to find the maximum velocity or minimum value of the velocity, instantaneous velocity and all from this graph, right? So we will start with the basic unit of calculus, which is concept of limits today. See, consider the situation we have a 50 centimeter of wire and we have to convert it into a rectangle with the largest possible area. So this is what are the dimensions of the rectangle. There are several ways to calculate this value, but here we are going to learn about the concept of limit using this problem. Okay, so consider a rectangle whose sides are, one side is let's say B and this one is also B in that case. So this length will become 25 minus B. Okay, and hence we can construct a area function in terms of B, which is length times breadth B times 25 minus B, which is 25b minus b squared. It's a downward facing parabola. We can find the vertex of this to get the maximum value, but I'm not going to use the algebra. We will use the concept of limit, means we will find a value of b approaching to that number. I will get a maximum value of the area. So for that we can construct a table for the different values of b. As you can see here, b as 12, the area value is 156, b is 12.2, area is 156.16, and if I keep increasing the value of b, my area value is increasing accordingly, but after 12.5 the area value starts to decrease. So as you can see, at this 12.5, I'm getting a maximum value, right? So from this table, I can say there is a possibility that I will get the maximum value at 12.5. So for that, what can I do? I can also find the value of this area in the neighborhood of that B point. All I'm saying is we can also choose B as say 12.5000000001, which is almost 12.5, but from the right side. So whatever be the area value I'm going to get from here for this value, we call that as right hand limit of the function. But if I choose a number which is 12.499999 and corresponding value of area from here is called left hand limit. If these two left hand limit and right hand limit are same, then we say that is the limiting value of the function and it is represented by this function. Area is represented by limit b approaches to 12.5. Approaches to 12.5, that clearly means it is not 12.5, it is almost 12.5, and that gives us 156.25. Okay, so in this way we can calculate the value of a function in the neighborhood. That is the concept of limits. Okay, now consider the different scenarios, like we have the graph of a function given by this, and there is a hole here, and again starts from here, and then there is another hole here. Okay, so this is the graph of the function and we have 3 points. Consider 3 points. Let's say one of them is 10, x value is 10, and let's say here x value is, let's say, 22 and x value as 30. So let's find the limiting values. If I say limit x approaches to 10 for the y is equal to, the graph is y is equal to f of x. So what's that? I'm trying to find the limiting value, means what's the value of this f of x in the neighborhood of 10. So as you can see, the corresponding value of y in the neighborhood of x equal to 10 comes out as 10. So this is the answer. Now the second case is if I have to find the limiting value of x when approaches to 22. So as you can see, there is a hole, but yes, hole is only at that 22 only. In the left neighborhood or in the right neighborhood, it means a value which is very close to 22 from either left or right, the value of the function y is equal to f of x comes out as what? This number which is 16. So the value is 16 here. Now in this way, let's talk about this 30. If limit x approaches to 30, as you can see, for the left neighborhood of this point, means if my x value is like 29.9999999, then the value of y is 20. But if I take a value x as 30.000001, then the y value is more than 20. It is not 20, right? It's like 24. So we, in this situation, we are not getting the same value. So we call limit does not exist for this, right? Using the graphical method, we can find the limit using this. Now, let's talk about this problem. Limit x approaches to 3, x squared minus 9 over x minus 3. So, first thing is direct substitution. If you put x as directly 3, what you will get? 3 squared minus 9 over 3 minus 3, which is 0 over 0. It's indeterminate. There are 7 indeterminate forms in total. 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, 0 to the power 0, infinity to the power 0, and 1 to the power infinity. These are 7 indeterminate form. If you get any answer like this, so we call that indeterminate form and value cannot be determined directly. So what we do is we try to find the value of the function in the neighborhood of that point. Either you can use graph or table. Okay, let's talk about the graphical way. X squared minus 9 over x minus 3. You can draw the graph of this function, okay, which looks like this. As you can see, there is a hole when x approaches to 3. But the thing is, what's the value of this function in the neighborhood of 3? Yes, it is almost 6. So we will say the limiting value of this function when x approaches to 3 for x squared minus 9 over x minus 3 comes out as 6. That's the answer. Consider this situation where limiting value of x approaches to infinity is to be calculated for 1 plus 1 over x raised to the power x. Okay, so let's use the tabular method. So what you can do is you can make an Excel sheet, find the values of the function for the different values of x, choose the values of x like 1 and keep increasing it. 1, 10, 25, 50, 100, 1000, 10,000, 1,000,000 and so on. So if you do this, you can see my values are starting from, in this case, 1, 2.5, 2.6, 2.6 something. And if I keep increasing the values of x, my y value is approaching towards this 2.718. If you take x as 1 million, 10 million, 100 million, you will find that value of x, value of the function is approaching towards 2.71828 something. So what can I say? That's my limiting value, right? When limit x approaches to infinity means it's a very, very, very large number. The value of this function which approach towards 2.7182818. Okay. So now let's talk about the instantaneous rate of change. So for that, consider the graph of a function. Here, time versus distance graph is given to us. A vehicle starts from 0 t equal to 0 to t equal to 3. Now, during this is the graph. So we are trying to find the average velocity for the entire journey. So we know the velocity or the average velocity we can find by taking change in values of distance over change in value of time, right? So here we have both things, time as well as distance. So at this point and this point, x value represents the time and the y coordinate represents the distance. So we can use average velocity for t equal to 0 to t equal to 3 comes out as y2 minus y1 over x2 minus x1, change in values of y over change in value of x. So that comes out as 133. Now let's reduce this interval. It's not for entire journey. Let's reduce it from time t equal to 1 to t equals to 3. And let's calculate the average velocity for this. So what we are doing, we are trying to find the slope of this chord, right? slope of this chord joining these two endpoints. So in this case, this value comes out as 166. Let's reduce the size. So from t equal to 1 to 2.5, we can again find the average velocity for this time interval for these 1.5 seconds in total. That comes out as 150. Now let's take this point 2.5 is so small that it almost approaches towards the initial point. So that value is called instantaneous velocity value. And in this case, it's not a chord, it will become a tangent line because both starting and end points are almost same. So that's the concept of limit. We are trying to make it make the difference as small as possible, and hence it is almost zero. The difference is almost zero. So we have here the tangent line, and its slope is given by change in value of distance over change in value of time, where both change in value of distance is zero as well as change in value of time is almost zero. So that is our instantaneous rate of change. That gives us the instantaneous velocity for the distance time graph, right? Okay. Now representation and interpretation. When you have a graph of function and you choose a point and calculates the tangent line, let's say this point is P having the coordinates x comma y over this graph y is equal to f of x, then we can represent the derivative by d over dx of y. That means rate of change of y with respect to x. We can also represent it by f prime x, or it is also the slope of tangent line at that point, which is gradient of the tangent line. And if the tangent line makes an angle theta with the x-axis, then this is also the tan theta, or you can say m, or gradient of the line. Okay, so all these all means the same gradient of the tangent line. We have a graph y is equal to f of x, and we are looking for the slope of tangent line, which gives us instantaneous rate of change of y value in this case with respect to x. Okay, now let's solve some questions. It says using the technology suggest the limit of sin x over sin pi x over 180 when x approaches to 0. X is in degree. So what can I do? In this case, we can use the graphical approach or we can use the tabular approach to get our answer. So with the graphical approach, we already know we can find the value of the function in the neighborhood of that 0 value, right? So let's use the tabular method also. So construct a table and choose different values of x. So if I take the different values of x and if I reduce it so that it approaches to what number? 0. So let's start from 10. So take x as 10, 5, 1, 0 0.1, 0 0.01 and so on. Means I'm trying to approach towards 0. And let's calculate the value of the function in that. Sine x over sine pi x over 180 for this value of x comes out as this as you can see in the table, and as you can observe the value of the function is approaching towards 1. If I keep decreasing and try to approach towards the 0, you can see the value of the function approaches towards 1, and hence I can say limiting value when x approaches to 0 for the sin x over pi x over 180 degrees, yes, it exists and it is equals to 1. Okay, you can also find the left hand limit if you want to, and that also will approach towards 1, and you can say in the limiting value is 1. Now let's solve a question on derivative. Okay, so the graph of y is equal to x square is given to us. This is the graph of y equal to x square, and we have 2 points P and Q. The coordinates of P are already given, which is 4 comma 16, and Q is a moving point. Okay, we will take different values of Q, like x value of Q is 5, 4.5, 4.1, 4.01. Means the uh, Q is a moving point on this y is equal to x square curve. Now they want us to find the estimate value of the limit of the gradient of the chord 4 comma 16, means we are looking for the rate of change when this p and q are almost same points, or we can draw a tangent line at that point, right? Okay, so we will start with the chord. Okay, we will start with this chord and let's find the values of these. Okay, fill the table. So here x values are already given. We can use the y is equal to x square to find the corresponding values of y. Put x equals to 4.5, 4.1, 4.01 to get the values of y here, right? That you can do using your calculator also. Now, after that, once you get these values like 20.25, 16.81, and 16.0801, and so on. Now, the change in values of x. The initial value of x is 4, and q values are given here. So, change in values of x, 4 and 5, change of 1. Between 4 and 4.5, change is 0.5. Between 4 and 4.1, the change is of 0.1. And you can see this, right? Now, similarly, we have the value of y. Initial value of y was 16, right? So we can find the change in values of y as well, starting from finding the distance between 25 and 16, right? Which is 9, and we can fill this column as well. Now, using these two columns, we can divide these two columns because we know the gradient is given by what? Change in value of y over change in value of x. That's the value of gradient. Correct? Now, let's fill this table and see what we are getting here. So when you fill this, you will get 9, 8.5, 8.1, and 8.01. As you can see, when my x value is approaching towards 4, the gradient is approaching towards 8, and that's the answer. So here I can say dy over dx when x is equals to 4, which is also our limiting value, right? We can say limiting value of x approaches to 4, then delta y over delta x comes out as 8, which is the gradient of the uh, chord, you can say, or tangent line basically in this case. Okay, so what does this limit tells you? You can see here the gradient of the chord is tending towards 8, and this suggests that the gradient of the curve at this point 4 comma 16, which is calculated using the concept of limits, is coming out as 8, means the value is approaching towards 8. Okay, so now we have covered all these things. Let's have a quick recap what we did in this session. So we started with finding the estimated value of limit of the function from a table. We also covered how to find the limit of a function using the graph by finding left hand limit and right hand limits, right? Next is we see the meaning and the notation for the derivative dy over dx and its representations. And next thing was interpret the derivative as a rate of change. That was our like for the time versus distance. In that case, the velocity was the rate of change of that. Now, interpret the derivative as a gradient function, delta y over delta x, as we have already calculated. And we have seen with the help of an example, how can we estimate the gradient at a point, right, as a limit of gradient of the chords. So that's it for today, and I'm giving you few exercise questions. You can try these questions all by yourself and keep watching, keep learning. See you all in the next session.